In this video, we are going to discuss the solution of higher order ordinary differential equations whose right hand side is of the form e power ax. The problem given here is solve d square plus 6d plus 5 of y is equal to 16 e power 3x plus 2 e power minus x plus 3. Let's start from the given equation. We are going to find the general solution of this equation. Let's start from the given equation. This is of the form f of d of y is equal to capital X. So here f of d is equal to the function in the left hand side. What is that? D square plus 6d plus 5. What is capital X? The function in the right hand side. Capital X is equal to 16 e power 3x plus 2 e power minus x plus 3. Now we are going to find the auxiliary equation. How to find the auxiliary equation? The auxiliary equation is f of m is equal to 0. To find f of m is equal to 0, we replace d is equal to m in f of d. Then what do you get? We get m square plus 6m plus 5 is equal to 0. Now we are going to find the roots of this auxiliary equation. For this, we choose two numbers whose product is 5 and addition is 6. We choose the number as 1 and 5. When we multiply, we get 5. When we add, we get 6. So by using these two numbers 1 and 5, we are factorizing this one. The factors are m plus 1 and m plus 5. So the roots are m is equal to minus 1 minus 5. Here we get the roots as real and different. By using this, we are going to write down the complementary function. The complementary function is equal to c1 e power m1x plus c2 e power m2x, where m1 and m2 are the roots of the auxiliary equation. Here m1 is equal to minus 1, m2 is equal to minus 5. We replace the values. The complementary function is equal to c1 e power minus 1x plus c2 e power minus 5x. Now we are going to find the particular integral. Particular integral is equal to 1 divided by f of d into capital X, which is the right hand side of the given ordinary differential equation. We replace capital X value. Now the last term 3 can be written as 3 into 1. That 1 can be written as e power 0. We separate the terms. Now we are going to use the rule of e power ax. That is, if we have 1 divided by f of d into e power ax, that can be written as e power ax divided by f of a. F of d can be replaced by f of a. That is, we are replacing d is equal to a. What is a here? The coefficient of x in exponential term. So that what is a in the first term? A is equal to 3. Wherever you find d, you make that as 3 in the first term. What is a in the second term? That is equal to minus 1. So we replace d as minus 1. What is d in the third term? D is equal to 0. So wherever you find d, you make that as 0. Now we are eliminating this one. First term becomes 16 e power 3x divided by 32. In the second term, our denominator becomes 0. So for this, what shall we do? We multiply x in the numerator. So we get 1x in the numerator. Differentiate the denominator with respect to d. So that d square becomes 2d, 6d becomes 6, 5 becomes 0. The last term becomes 3 e power 0 by 5. Now again in second term we are replacing d is equal to a, which is minus 1 here. We eliminate this. This is our particular integral. The general solution is complementary function plus particular integral. We replace complementary function value and particular integral value. This is the general solution of the given ordinary differential equation. Let us summarize. The given equation is of the form f of d of y is equal to x. We find the auxiliary equation by replacing d is equal to m. We get f of m is equal to 0. We find the roots of this auxiliary equation. Here we get real and distinct roots. By using this, we are going to write down the complementary function. The complementary function is equal to c1 e power m1x plus c2 e power m2x. To find the particular integral, we start with 1 divided by f of d into x. If we get 1 divided by f of d into e power ax, we just replace d as a. So we get e power ax divided by f of a. This is when f of a is not equal to 0. If f of a is equal to 0, we multiply an x in the numerator and we differentiate the denominator with respect to d. And again we substitute d is equal to a. We continue this process until we get f of a not equal to 0. We get the general solution as y is equal to complementary function plus particular integral. Replace complementary function value and particular integral value. We get the general solution.